Here is our day 5. Here is the assignment. Here's the assignment as it looks in Google Classroom. Notice that we are going to continue with some of the Lewis dot structures. That was the last week's ed puzzle that I threw up as kind of a preview of what we're going to start doing this week. We're going to start talking about the differences between ionic and covalent bonding. We've already brushed on those a little bit in comparing bond characteristics, how you can recognize ionic versus covalent bonds. And we've done a near pod on each about their different bonding tendencies and how they function. And we're going to be diving a little bit deeper on that with this simulation today. So on the left side of my screen, I have your document over here that you're going to be doing your work in. And on the right side of my screen, I'm going to be, I have the link up that is going to be the simulation that we are going to use in this assignment. So let's run over the IA real quick and just discuss some of these answers. Can anybody describe to me, just off the top of their heads, the difference between an atom and a molecule?
I said that I said atoms are what make up molecules, and yeah, just like I guess the atoms are smaller than molecules.
I mean, you're not wrong. That's true. Atoms are individual pieces of an element. Okay, molecules are individual pieces of a substance. But the key difference between an atom and a molecule is that a molecule can have multiple atoms bonded together. That's your key difference, is that molecules have multiple atoms bonded together. Where are our metal atoms located on the periodic table? And where are non-metal atoms located on the periodic table? This is just a callback to reading the table. Anybody know? Ruby, is that a hand?
Yeah.
Okay.
The metals are on the left side, and yeah, and then the metals are on the right.
Absolutely. This black line right here, our semi-metals fall along that black line. Anything on the left side is going to be metallic in character. Anything on the right side is going to be non-metallic in character. Good memory. So what are these subatomic particles that participate in bonding? Subatomic particles are the particles that make up our atoms. That would be protons, neutrons, and electrons. Which ones are responsible for chemical bonding?
I will give an answer in the chat.
Oh, thank you. Yes, Awa, electrons. I missed that. Thank you. Yes, the electrons participate in bonding, specifically our valence electrons, the electrons on the very outside. How can you determine the number of valence electrons using the periodic table? There's a couple different ways we can do this, but what is one way?
The number of valence electrons
Yeah, how can you determine it?
in the group.
By the
Yeah,
group?
the main group numbers.
The main group numbers. You got it. Forget our transition metals. But group 1 has 1 valence electron. Group 2 has 2 valence electrons. Group 13 has 3. Group 14 has 4. Group 15 has 5. So we know by that trend, that pattern. Also, if we zoom in, we can look at the electron configuration and read the valence number right off of the table. So I'm not going to write that answer down because I just showed you. And then how to draw Lewis dot structures. These are here for you guys to practice because you're going to be doing a little Lewis dot structures drawing already or later in the assignment. So I have these things embedded as Google Drawings so you can double click on them, open them up, and then edit them. So if you wanted to make carbon a valence structure for carbon, look at our reference table. Carbon has 4 valence electrons. So I'm going to create a shape. I'm going to make a circle. I'm going to make a little dot. I'm going to make it black just for that. I'm going to make it red so it shows up easier. And I'm going to make 4 of them. And I'm going to place them around carbon. And the way I made 4 of them was just copy, control, paste. Control, copy, paste. It's nice and straightforward. And I can just use my arrow keys to move them around. If you're on an iPad, You can just click and drag them around with your finger. Pretty straightforward. There you go. So there is a little sloppy, but a Lewis dot structure for carbon. The chemical symbol with 4 electrons around it, representing the four dots representing 4 valence electrons. So if you guys want to practice that in your IA, it'd be a good idea because you're going to be doing more of it later on in the assignment. And that's what we're going to get to now. By the way, if you need me to zoom in on this document so you can see it better, so you can read the questions better, just let me know in the chat or just unmute yourself and shout out, hey, can you zoom in so I can see that question? So now we're going to get into the actual activity. So if we look at the Google Classroom, there's this link and there's the document. So what I suggest you do when you do this, whether you're on an iPad or you're on a computer, is you split your screen like I am doing right now. And you have the questions up on one side and the simulation up on the other side so you can follow directions and fill things in. So I'm going to do part 1 or some of part 1 with you guys right now, fill it out, show you how to use the table, how to use the simulation, how to answer these questions. And then I'm going to let you do the rest of it on your own. So if you haven't been paying attention to this point, you should really be paying attention now. So I have the simulation up. I'm going to look at the first question. It says choose sodium, Na. So the green blocks over here can be selected, highlighted. So I'm going to click on sodium, and it brings up a little element card here. Shows me the element type. It's a metal. Shows me the electronegativity, 0.93. That's pretty low. Remember, 4 is the highest, 0 is the lowest. And it gives me the Lewis dot structure of sodium. Sodium has 1 valence electron. So what type of element is it? It's metal. How many valence electrons does it have? 1. Pretty straightforward, okay? So now it wants me to choose fluorine. So I can also click on fluorine. 2 tabs is the most number of little tabs that you can have on this simulation. You can have up 2 elements at a time. So fluorine is a nonmetal. How many valence electrons does it have? Well, I count 1, 2, 3, 4, 5, 6, 7, 7 little dots. So that's 7 valence electrons. Notice how when I did carbon, this is just a little review from the ed puzzle you did last week. Carbon has 4 dots that are evenly spread out. You want to spread out your dots, so we go 1, 2, 3, 4, and then fill in. Remember, we're getting to the octet rule. We want 8 valence electrons around our atom. So we're almost there with fluorine. We're almost there with 2 electrons on every side. Let me check the chat real quick. Yeah, you can only click on the elements that are highlighted. This simulation is tailored to this activity that we're doing. So what type of bond are these elements going to form? And you can see this right here. So before I click and test, I would like somebody to think back to last week, thinking about ionic bonding. What types of elements create ionic bonds? Is a metal and a nonmetal going to create an ionic bond, or is a metal and a nonmetal going to create a covalent bond?
I think it's an ionic bond.
These are gray squares. Okay, so why are you saying ionic bond? It sounds like now more people are leaning toward ionic bond. Why are we leaning toward ionic bond? Now we're splitting back and forth. Now I have more people going covalent. So let's break down the words. In ionic bonding, the root of that term is the word ion. An ion is a charged atom, an atom that has given up or received an extra electron. So now it has a charge on it. If we break down the word covalent, co meaning together, valent referring to valence electrons. Does that ring any bells? Does that bring anything back?
So would it be covalent?
I don't know. Let's check. If we click covalent, that is not correct. That simulation will tell us it's not correct. If we click ionic, that is correct. If it allows us to advance, that will tell us that yes, this is an ionic compound. Ionic bonds always form between metals and a nonmetal, something that wants to give up its electron, something that wants to accept the electron. Metals have low valence electrons, nonmetals have high valence electrons. They want to take from each other so that they can reach that octet rule and be stable. So I'm going to show you the reference table again. Sodium had 1 valence electron, and fluorine had 7 valence electrons. This is another callback to last week. If sodium and fluorine were going to bond together, how many atoms of each would we need in order to create a balanced ionic compound with a net charge of 0? I'm going to look at over here, and I see that fluorine has an ionization charge of -1, oxidation state of -1, because it wants to gain 1 electron. Sodium has a charge of +1 because it wants to give up 1 electron. So over here, we're only going to need, I forgot about over here, we need to highlight this. Okay, so this is going to be an ionic bond. How many atoms of each? I think it's going to take 1 sodium and 1 fluorine. And then you can submit your answer, and it will tell you if you're correct or not. So we see here is that sodium is going to become a positive ion. Fluorine is going to accept its valence electron and become a negative ion. Those positive and negative charges hold themselves together, and this becomes sodium fluoride. So it's an ionic bond. We need 1 sodium and 1 fluorine atom. The equal and opposite charges will balance each other out. So Ford just has us watching the simulation that I'm demonstrating right here. Watch the final animation closely. It will play continuously, as you see right here. Describe the change the number of valence electrons in the atom as the bond is successfully formed. There's no trick question here, okay? I'm just getting you to write what you're seeing and verbalize. You can say it out loud to yourself if that helps, but get down in a written form to help you remember what is happening here. Describe the change in the number of valence electrons. So, well, for sodium, it is losing its only valence electron and becoming positively charged. Fluorine is gaining 1 valence electron and becoming negatively charged. Forgive my typos. So what is the purpose of this? Well, they are satisfying the octet rule. Both atoms now have 8 valence electrons. It may look like sodium has 0 valence electrons, but I'm going to bring it back to the reference table to highlight the fact that sodium has a configuration of 2-8-1. So if we get rid of that 1, now sodium has stripped its outer layer and is nice and stable and happy with an outer set of 8 valence electrons. What does the positive charge indicate? Mentioned subatomic particles. Positive charge indicates that electrons have been lost. What does the negative charge indicate? Electrons have been gained. What's the final overall charge? Well, what is the final overall charge if we have a +1 and a -1? What is +1 and -1 equal to?
0.
0. Sorry, I monologued there for a second, but I want to make sure you guys are still paying attention. Yes, +1 and -1 equal 0. I could probably write that a little more gracefully. Let's do it like this. +1 plus -1 equals 0. When we put those two elements together, we get a net charge of 0. What is the name? Sodium fluoride. So this simulation is really nice because you cannot mess it up. If you select sodium and fluorine and you select the wrong bond type, it will let you know that it's the wrong bond type. If you select 2 sodiums and 1 fluorine, it will let you know that is not correct. So you can trial and error your way from the start to the finish. Also, let's keep in mind that if we select say, magnesium and fluorine, still going to be an ionic bond because still a metal and a non-metal, but we don't have equal charges here. So 1 magnesium is going to have a charge of +2. It's in our reference tables here. Also, we see that it has 2 valence electrons to give away. So we're going to need 2 fluorines. So our simulation will change as 1 valence electron from magnesium is going to each of the fluorines. So I gave you a pretty quick overview right here, but I think this will be really good practice for you to hammer home ionic and covalent bonding as you're guided through this simulation by this worksheet. The answers are not trick questions. They are as straightforward as they seem, right? We're just trying to I am trying to help you make the mental connections between valence electrons, bond type, the type of bonds, and also we're reinforcing the naming of these bonds, of the compounds. When we have a final compound, what do we name it? What do the formulas look like? What are the valence electrons doing? This is the delicate dance. This is the dance that all elements, all atoms, everything in the world is doing constantly. Every time you eat food, you're eating chemical compounds that go down into your body that get broken up into their individual ions. Some of them are used as electrolytes. The energy from these bonds breaking is harnessed and used to run your body. You breathe in the covalent compound oxygen. Your body uses that oxygen in your blood, converts it to carbon dioxide. You breathe back out carbon dioxide, another covalent compound. So there's this delicate dance between ionic, covalent compounds, and all the atoms in the universe that are constantly changing and moving between bonds with each other, from ionic to covalent bonds, trading electrons, sharing electrons. This is the basis for everything around you that you see constantly, what is happening on a molecular microscopic level. And understanding the function of how these atoms interact with each other is really fundamental to understanding why anything in the world happens ever. So, at the risk of pontificating, to avoid the risk of pontificating too much more, I'm going to stop.